Okay, so for this last lecture, we're going to look at planets around other stars and the role that radio astronomy can play in this very fast-moving and exciting field. So just going to recap a little bit on how we detect planets around other stars, then see what we can learn from radio emission from the planets in our own solar system, principally Jupiter, and then look at the potential for radio detections of exoplanets. And I'll finish up with the intriguing topic of looking for intelligent life through radio telescopes. So Catherine touched on this a little bit in her lectures, but just to recap here. So the first planets around other stars, so we're not talking about planets around our own sun here, we're talking about planets around other stars, were discovered with the so-called radio velocity technique. And this is where you take spectra of the parent star and look for the motion of the star, because the planets themselves are so faint that you don't see the light usually directly from the planet. So this is an indirect method. You look for the motion of the star around the center of mass because of a planetary body in orbit around the star. So we can see that in action on this little schematic here, sort of exaggerated scale. So if you've got a very low mass body orbiting a high mass body, so a planet going around a star, then there will still be a common center of mass between the two, but because of the mass ratio, that center of mass might actually be inside the star, but it still wobbles around a little bit with the period of the planet. And it's that motion that you're looking for with the Doppler shift. So that's illustrated in this little diagram, moving diagram here. So here we've got the star, not the planet, star going around its center of mass. Okay, ignore this in the middle here. If we just look at the bottom here, this is what the radio velocity technique is all about. So this is just a schematic showing that the spectral lines in the spectrum of the star will be periodically shifting to and fro in wavelength, because they'll be blue shifted when the star is moving towards us and red shifted when it's moving away from us. So that will give this telltale sign in the spectrum. And that was done back in the 90s with the first planet discovered this way. 51 Pegasi b, so 51 Pegasi is the star that we're looking at, and the planets are called by little letters, starting with B. And so you can see that this is what's called a radio velocity curve. So it's a plot of the radio velocity deduced from the Doppler shift as a function of time. And so you can see that there are variations here that vary basically sinusoidally, so that you can measure the amplitude of the sine wave here, and it's about 57 meters per second. So normally in astronomy, we were used to dealing with radio velocities that were, kilometers per second or larger. And so these velocity shifts were very small, which is why it took, advances in technology and calibration to measure these very small shifts, Doppler shifts in the spectral lines of the star. But from the amplitude and the period, so you see the period here, only 4 days. So again, this is very surprising for this initial discoveries, but you can translate that into a mass, and it was about half the mass of Jupiter. And there is also an uncertainty because we don't know the orbital inclination angle, I, here, and so we normally leave that in. So if on average that is around about a half for randomly orientated systems, then you could probably double that. So basically this was a Jupiter mass planet, but in a 4-day orbit, as opposed to Jupiter in our solar system, which is in a many-year orbit. I can't remember. Okay, so you might have been thinking, can we just go and directly look for planets around other stars? So you can, and it has been done. So here is a nice example where you can actually see a time sequence of images. So these images are made in the near infrared. They're made with this adaptive optics technique that takes out the turbulence of the atmosphere and delivers near diffraction limited images. But the other thing you need to do is block out the light from the central star. So that's what this dark disk in the middle here is all about, so that you can still see a lot of artifacts in the middle here left over from the very bright glare of the host star. But you can see these 4 faint objects are clearly detected, and over the period of time here, period of several years, you can see that they are indeed orbiting around the star, and they are in Keplerian orbits. So the one closer in are moving around faster than the ones further out. So this is a beautiful illustration of this. This is the scale in this system here. So that's 20 astronomical units. So again, the outermost planets in our solar system are about 30 AU from the star. So these are, again, unusual. This time they're unusually far away from the star, as opposed to the previous rate of velocity detection, which was unusually close to its star because its period was so short. But at the moment, most planets are being discovered by a method called transits. And so this is where the planet passes directly in front of the star, and so blocks a tiny little bit of its light. Okay, so you can see that illustrated in the cartoon below. Of course, we don't see any of this detail because you can't resolve with a telescope like the disk image of a nearby star. All you're really doing is in the graph below. You're just monitoring its brightness as a function of time. So this is referred to as a light curve. So you're looking for a little dip in the light curve. And obviously you want that light curve to repeat every time the planet goes around the star. So you might have to wait a long time for that repeat. Okay, but you'd never be sure if you saw one of these little dips that it was due to a planet or something else. So you have to look for repeated small dips. They have this characteristic shape, and that's what you look for. So that technique has now been very successful and has delivered thousands of planetary detections. And the real breakthrough here came with what's called the Kepler satellite. So that was a mission that basically optical telescope just stared at one bit of sky where there were lots of stars. So it's looking along the Milky Way. And it basically just stared at 1,000 stars for 2 or 3 years. Okay, and just monitored their brightnesses, but it did so extremely accurately. And so you can see in this little example in the bottom left here, this is a light curve from the Kepler data. So you can see one of these characteristic little dips, but you can see on the scale here that the flux, the brightness of the star, has only dropped by 0.05%. Okay. So this is incredibly accurate work, which you can only do from space. And so from this, obviously you measure the period again. You don't measure the mass directly here, but you do measure the size of the planet, because the size of the dip here is proportional to the relative area of the planet doing the eclipse relative to the star itself. So the depth of the dip tells you the size of the planet, radius of the planet, because you can usually estimate the radius of the star. So that's enabled many extremely interesting planetary systems to be discovered. And so one example here, so this is one of these planets referred to as Kepler 22. So you can see relative to the size of our solar system, you can see where this planet lies. And it's a planet that's somewhat bigger than the Earth, a couple of times bigger. But it's also in what is referred to as the habitable zone of a star. Okay, so a habitable zone for a planet is described as the range of distances away from the star where liquid water could exist on the surface of the planet under certain assumptions. Okay, so we think that liquid water is a prerequisite for life here on Earth, and so the likelihood is that therefore it might well be the basis for life elsewhere in the galaxy or the universe. And so finding planets in their so-called habitable zones of their stars is one key aim of planet searching. And so this particular planet is in the habitable zone of this particular star. And a key result from Kepler, which is, it's still astonishing every time you say it, is basically that we now believe that all stars pretty much have planetary systems. Okay, so every star you look up at the night sky at has probably got planets orbiting it. So how did it come to deduce this? Well, Kepler looked at 100,000 stars and it found transits around a certain percentage of them. And of course, in order to see a transit, the orbital plane of the planet has to be aligned with our line of sight. Otherwise, we would not see any little eclipse by the planet of the star. But once you know the sort of distribution of planetary orbits and sizes, you can work backwards to, work out what fraction of stars should have exhibited eclipses for certain assumptions. And basically the assumption is that, at least 70% of stars have planetary systems. And there's enough uncertainties on that it's probably safe to assume that they all do. So that's a remarkable discovery, really, that all stars have planets around them. And here is the final result from Kepler in terms of the distribution of sizes of planets. So they did indeed find Earth-like planets, which was part of the initial goal. So very tiny drops in the light. Quite a lot of these so-called super-Earths, and the big gas giant planets like Jupiter, even though the initial radio velocity techniques were finding a lot of these, they're not so common as evidenced by the transit observations. Okay, so we can show this in another way. So this diagram is a little bit more complicated, but it does show you the types of planets that are out there. So each dot on here represents a planet that has been discovered. I think the red ones are ones that have had their mass measured by the radio velocity technique. And the blue ones are mostly the Kepler results and have had their mass inferred from their size. So, but you can see that there are quite distinct patterns on here. So this is a plot of the mass of the planet versus its period. And because of Kepler's laws, then the period really represents how close to its parent star it actually is. Okay. So they split into three groups. Up here, we've got these very unusual planets, or at least unusual as far as the solar system is concerned, in that they are Jupiter mass planets. You can see Jupiter here is about 300 times the mass of the Earth, but they're very close in, much closer in even than the orbit of Mercury in our own solar system. So these are the ones orbiting with periods of just a few days around their parent stars. We are now beginning to pick up Jupiter-like planets that are in more Jupiter-like orbits as compared to the solar system. And so you can see those here. So similar to sort of Jupiter and Saturn. Okay, again, not quite so far out yet, but there are reasons for that. And then there's a big, most of the Kepler planets were down here. So these are what are referred to as super-Earths, also referred to as rocky planets. So they are they're much smaller than the hot Jupiters, and they orbit fairly close in. Okay, so again, similar to sort of Mercury's orbit, something like that. Well, even Mercury's orbit's out here, a period of 88 days. So fairly close to the parent star. And you can see on here that although Earth mass planets have been discovered, they're here, none so far as far out as Earth yet. Okay. So looking at this, you might think that maybe it's our solar system that is unusual, but we need to think about whether that's real or just selection effects. And another little aspect here that's very important is, if we're finding all of these type of planets, is there any way of working out what they're made of and whether they might be capable of hosting life, for instance? Do they have oxygen in their atmospheres? Well, it's possible to try and do this. So if you, during the transit, the light from the star will be passing through any atmosphere that the planet has. And so if you compare a spectrum during the transit to a spectrum off transit, you can look at the difference. The differences will be very, very small, but if you can do this accurately enough, then you can basically get a spectrum of the atmosphere. And if you can get a spectrum of the atmosphere, you can work out what it's made of. You can also do this in the infrared, do the experiment in reverse, so that when the star eclipses the planet, then any thermal emission by the atmosphere of the planet will disappear. So again, you can look at the difference and do it that way. And so this has been done. You can see some examples here. So things like water vapor and ozone have been discovered, CO2 in some of these planetary bodies. And so you can start to diagnose the composition of the atmospheres of these planets. This is something that the new James Webb Space Telescope, the successor to the Hubble Space Telescope, which is a big telescope in the infrared in space, is going to be doing a lot of this kind of work. So watch out for those results when it gets launched very soon. Okay, so that's sort of planet detection and a little bit about planet characterization. And you can see that I've been talking about sort of optical and infrared techniques to date. So we'll just have a little break here before we start to look at where the radio comes in. During the break, perhaps take 5 minutes to discuss why it's so difficult to detect planets similar to the Earth around other stars.